Thank you. So there's a couple things I want to say up at this front here. So first of all, thank you to Martin and Andreas for inviting me. It's a pleasure to speak in this seminar. The second thing is, like, please feel free to interrupt me with any questions or you want during the whole at any point during the talk, because I've sort of planned a pretty leisurely talk here, and I don't I'm happy to get derailed. And then probably the third thing I should say is that this is a two-parter. Kalen is going to be speaking after me, and so I'm not really going to be talking about any techniques in this talk. I probably won't even say the word tropical, except for just now. So just that's so if you're wondering where's all the tropical geometry, you just got to wait a bit. Okay, so let's get started. Okay, so I wanted to start with, what is this? How do I make this go away? That doesn't matter. Okay. So I wanted to start with sort of the basics of what is Brill-Noether theory. So Brill-Noether theory is about the study of algebraic curves. In particular, the motivating question behind Brill-Noether theory is, if you give me an algebraic curve, I want to describe all of its maps to various different projective spaces, right? So, if you were a 19th century algebraic geometer, you would think of a curve as coming equipped with an embedding in projective space. That would be part of the data of an algebraic curve. But in modern times, we think of a curve as an abstract object, and it makes sense. It's interesting to ask, what are all of the different ways you could embed it in projective space, or what are all the different ways that you can map it to projective space? Okay, so this is the same. You can reformulate this through some standard algebraic geometry stuff into a question about line bundles, right? So given a map from a curve C to projective space, you can pull back the tautological bundle on projective space, pull back O(1), and that'll give you a line bundle on your curve, right? And if the curve sits inside PR and it doesn't sit inside any, the image isn't contained in any hyperplane, then that line bundle will have at least R+1 global sections, independent global sections. Okay. And conversely, if I give you a line bundle and I give you a subspace of global sections of that line bundle, then you can choose a basis for that subspace, and then the map, and then you get a map from the curve to projective space by just coordinate-wise plugging in that basis. Because it's a line bundle, that map only makes sense, is only defined up to simultaneous scaling of all of the sections. So it doesn't give you a map to an affine space, but it does give you a well-defined map to a projective space. And so you see there's this there's a correspondence between line bundles on one hand and maps of projective space on the other hand. So for the rest of the talk, I'll talk about line bundles. Okay, so I can now reformulate. I can reformulate the question above in terms of line bundles, right? So the Brill-Noether variety is defined to be, the Brill-Noether variety WRD is the space of line bundles on your curve of degree D that have at least R+1 independent global sections. And so WRD is, you can, by everything that I've said above, you can alternatively think of it as, morally the set of maps from your curve to projective space of dimension R of degree D. And so the question that I started out with can be reformulated as just given a curve C, describe all of these varieties WRD, right? What do you might want to know various things about them, their dimension, how many components they have, are they smooth, stuff like that. And so those are the kinds of questions that I want to talk about today. Okay. All right, so so those sorts of questions, there's, how should I phrase this? There's so the kinds of questions that I was just posing have known answers in the case where C is sufficiently general in the moduli space of curves. So if C is a general curve of genus G, then I define this number rho of GRD. It doesn't really matter what it is. It's G minus R plus 1 times G minus D plus R. That's, R plus 1 is H naught of your line bundle, and G minus D plus R is H1 of your line bundle. So this is G minus H naught times H1, all right? But, forget about the numerics. What this number rho is it's the expected dimension of the Brill-Noether variety WRD. Okay, and so this series of results from the late 70s and early 80s tells us about the geometry of WRD when the curve is sufficiently general. In particular, the variety has dimension, the dimension of the variety is the expected dimension when the expected dimension is non-negative, and when the expected dimension is negative, the variety is empty. That's the Brill-Noether theorem proven by Griffiths and Harris in 1980. If you look at the set of line bundles whose such a H naught is exactly R plus 1, not larger, that locally closed variety is smooth. That's known as the Giesecke-Petri theorem. It was proven by Giesecke in 1982. If the expected dimension is at least 1, then this variety is irreducible. Proven by Fulton and Lazarsfeld. And what happens if the expected dimension is 0? Well, then the variety is a bunch of points. And you could ask how many points, and this is the answer. So if the expected dimension is 0, then WRD consists of exactly this strange number of distinct points. So, taken together, these results and possibly a few others are thought of as the standard results of Brill-Noether theory, and they tell you essentially everything that you could possibly want to know about WRD of C when C is a sufficiently general curve. Okay. So the first thing I want to do before I move on is I want to take these results, well, some of these results, and recast them in a combinatorial way. This is a bit of foreshadowing for Kalen's talk. I'm not really going to get into the details of where these combinatorial constructions come from, but this will just help me formulate some things later. So I want to think about a certain partition, which is just, or a certain Young diagram, which is just a rectangle with R plus 1 columns and G minus D plus R rows, right? So the total number of boxes in this Young diagram is R plus 1 times G minus D plus R. Then the Brill-Noether theorem can be restated like this. So you take a sufficiently general curve in MG, then the codimension of WRD in the Picard group is just equal to the number of boxes in that rectangle, right? Or equivalently, it's equal to the rank of this partition in the Young lattice, because the Young lattice is the lattice where the elements of the lattice are partitions, right? And one is less than another if the one is contained in the other, and the rank of a partition in the Young lattice is just the number of boxes. So this is just saying that so this is just I haven't really done much here, but it's a helpful formulation. And also, so that number I mentioned, so when the expected dimension of WRD is 0, then WRD is a bunch of points. And how many points is it? Well, it's equal to the number of standard Young tableau on this particular partition, so on this rectangle. Or stated in the lattice way, it's equal to the number of maximal chains in the Young lattice that start at the empty partition and go to the to this rectangle. Okay, so this is just a bit of foreshadowing, some combinatorial stuff. Okay, so this work that I've been describing is like basically was basically all done in the 80s. And so now I want to talk about things that people have been thinking about more recently. So these were all results about curves that are general in the moduli space of curves. But what if I have a curve that's not general? What can I say about its Brill-Noether varieties then? Okay, so one way to make a curve not general is to okay, so yeah, let me say that in a better way. So if you have a curve that has a map to P1 of sufficiently small degree, then it won't be general in the moduli space of curves by the results I was just mentioning. So let's think about curves that have some low degree map to P1, and to phrase this a little bit better, the way that it's posed on the slide is a little better phrasing, right? So given us a general cover of P1 of degree K and genus G, what can I say about the Brill-Noether varieties WRD? And it turns out that at first glance, it seems like you can't say much about these Brill-Noether varieties. They exhibit all sorts of pathological behavior that you don't see for general curves. So the WRD can be singular. It can have multiple components. The components can have different dimensions. Everything seems to go wrong. So here's an example. So if you take a curve of genus 5, if you take a trigonal curve of genus 5, so that's a curve of genus 5 that has a degree 3 map to P1. And then I want to think about what are all the line bundles of degree 4 and rank 1 on that curve. Well, one way I could get a line bundle of degree 4 and rank 1 is I could take my line bundle of degree 3 and rank 1 and I could add a base point to it. And you can see that, so that gives you, so for every point on the curve, you get a point, you get such a line bundle, and the so that's one of the components that I've pictured here, right? Is things, you take the G13 and you add a point. So you get a component that's isomorphic to the curve. Also, if you take any such line bundle and you take its Serre dual, it will also have degree 4 and rank 1. And so that gives you another component of W14 that is also isomorphic to the curve, and that's the lower one that I've pictured there. And it's not too hard to see that these two components intersect in exactly 2 points, right? So you set G13 plus P equivalent to K minus G13 plus Q, and then you solve and you see that there's exactly one pair P and Q that make that possible. It's a little bit harder to see that all of the line bundles of degree 4 and rank 1 on the curve are of one of these two types. There's different ways you could do this. You could use the base point free pencil trick. Yeah, so but it turns out to be true. So W14 looks like this, and in particular, you see it has 2 components. It's singular. This is a case where the components have the expected dimension, but we're already starting to see some bad behavior that we didn't see when curves are general. if you want, let's see, did I put this on the next slide? No. So if you want a case where it can have multiple components of different dimensions, you can just go up one genus. So look at curves of genus 6 and gonality 3, and then look at W14 for that curve. And what you'll see, if you work it out, you'll see that you get one component of dimension 1 that looks like this one. You take the line bundle of degree 3 and you add a base point, but then it also has a second component that's just an isolated point. So you can see all sorts of pathological behaviors when you start looking at these objects. Okay. Okay, so I should take a moment to talk about prior results along these lines. So the case where, very old case is due to Clifford in the late 19th century, who completely characterized line bundles of given degree and rank on hyperelliptic curves. Those are curves where K is 2. You have 2-to-1 map to P1. In the 40s, Moroni essentially solved this problem for the case of trigonal curves. Moroni has an interesting story, maybe I won't get into today. But if you want to understand the Brill-Noether theory of every single trigonal curve that's out there, you can look. There's a recent paper by Hannah Larson that completely describes the Brill-Noether loci for all trigonal curves. I think that's the title of the paper, actually. And so that was the state of the field for a long time. People knew how to handle the case of hyperelliptic and trigonal curves, but not really for K larger than that. So there was, in the early 2000s, there was partial progress by various people on the cases of K equals 4 and K equals 5, Copens, Martins, and Park. In 2002, Copens and Martins found components of WRD that have unexpected dimension in these cases. I first got interested in this question after Nathan Flieger published a paper in 2016 on using tropical methods to look at problems like this. So he provided an upper bound for the dimension of the largest component of WRD in this setting. So when C is a general degree K cover of P1, and the next year in a paper with Drew Varanganathan, we showed that Flieger's bound is sharp, so that the largest component of WRD actually has the dimension that Flieger predicted. But as we've seen, right, the WRD can have multiple different components in these cases. So this doesn't really completely solve the dimension problem, right? So in my opinion, the most exciting work has come since 2019, when Kalin and I and Hannah Larson independently discovered sort of the key idea that makes this whole story run. So I want to talk about that. Okay, so what the key idea is really these splitting loci. So really, in this setting where your curve is a degree K cover of P1, the varieties WRD are not really the right thing to look at, and I want to explain. So first, I want to give just a bit of notation. If I have vector mu mu1 through mu k, then I'm just going to write O of that vector as shorthand for this direct sum of line bundles, O of 1 of mu1 plus O P1 of mu2 and so forth. All right. Okay, so if I have a map from C to P1, I can look at this locus of line bundles on the curve whose push forward to P1 is O of mu, right? This is a locally closed variety. It's okay, and what I want to encourage you to think is that these splitting loci are sort of the natural analogs of Brill-Noether loci in this setting where the curve comes with a map to P1. And part of the reason I say that is because of what's written here. So the splitting type of line bundle determines its rank and degree, and it also determines the ranks of all the twists. If you take L and you twist it by some pullback of a line bundle on P1. So because of this, the splitting type is a more refined invariant than the rank and degree of a curve.
So you said they're locally closed. Can you sort of say that the closure of such a splitting locus is like a union of other splitting loci?
Yeah, so so I think that what's true, so if you look at, there's sort of a partial ordering on these vectors mu. That's like it's related to the dominance order in partitions, and and if you look at the set of line bundles whose push forward is O of mu or O of something that's larger than mu in this partial ordering, that's a closed variety. It's not necessarily the closure of this variety, but it is when C is sufficiently general. Yeah. Okay. So if we go back to our example, I think that's the next thing.
Sorry, Dave, can I just ask a follow-up question there? What did sufficiently general mean there? Does it mean in the sense of the map?
Yeah. So I mean, if the pair C comma phi is general in the Hurwitz space. Yeah.
Okay, and that's what you're proving your theorem about, right? Or...
Yeah.
Okay,
That's right.
Great, thanks.
Yeah. Other questions? Okay, so I'm realizing now that this picture is upside down from the previous picture. So, but let's go back to our example, a curve of genus 5, a trigonal curve of genus 5. So there are, how do I want to say this? Excuse me. So, you know, by push pull, H naught of your line bundle is going to be equal to H naught of the push forward of that line bundle to P1, right? And so if you want a line bundle that has two, you know, that has H naught equal to 2, then you need the sum of the non-negative numbers in your splitting type plus 1, you know, the sum of the non-negative numbers, each one plus 1 has to be 2, right? And so you see, and then the fact that the degree is 3 means that these 3 numbers should add up to 3. And so if you look at triples of numbers that satisfy those conditions. Well, there are actually a lot of them, but there are three that are sort of interesting in this case. So here they are, you know, -3, 0, 0, -2, -2, 1, and -3, -1, 1. And you see, if you look at the bottom one, -2, -2, 1, that has the property that if you subtract 1 from everything, you still have a non-negative entry. And so that has the property, so put in another way, that has the property that if you subtract off the G13, the line bundle is still effective. So and then the Serre duals of such line bundles have splitting type -3, 0, 0. And then in this partial order that I was describing earlier, -3, -1, 1 is less than or equal to the other two splitting types in this order. And so what you see is you have these three locally closed strata. Each of these are smooth. Each of them are irreducible. And as long as the dimension is at least 1, each of them is smooth, and as long as the dimension is at least 1, each of them is irreducible. So these strata are a better thing to look at than the whole variety WRD. Okay, I feel like I kind of botched that. Any questions about the example? Okay, so let's get to the theorem that was, okay, so this is going to be like the standard set of results in Brill-Noether theory, but in this setting where the curve comes with a fixed map to P1. Sorry about that, let me get rid of that. Okay, so let's be a general cover in the Hurwitz space HGK. And then I use this notation like mu with bars around it to denote the expected codimension of the splitting locus, which is one way of writing that is H1 end of O of mu, but here's a very simple formula for it. Okay, so then the first thing here was proven independently by Hannah Larson and by Kalin and myself. So the locally closed variety, the splitting locus has pure dimension G minus size of mu when this is non-negative, and it's empty when this is negative. In her paper, Hannah Larson also proved that these locally closed varieties are smooth. And then in a more recent paper of Hannah's, together with her brother Eric and Isabel Vogt, they show that if the expected dimension is at least 1, then these varieties are irreducible. And they also show that in the case where the dimension is 0, that, well, I'll explain on the next slide. There's a combinatorial interpretation for the number of points in these varieties. And I haven't written it here, but also there's a containment relation among these varieties that like one splitting type locus is contained in the closure of another splitting type locus if and only if the first is less than or equal to the second in this dominance order on the vectors mu. Okay, so taken together, these should be seen as analogs of the standard Brill-Noether package, but in this Hurwitz setting. Okay. Okay, so now I want to talk about the combinatorial interpretation of of some of the things that I just said. And again, this is more foreshadowing for Kalin's talk than anything else. So if I give you a splitting type mu, just one of these vectors, there's an associated partition, lambda mu, which I won't tell you what it is, but it's a special type of partition that's known as a K-core partition. We sort of I mean, I'll tell you a little bit of the history of us studying this. Like, we kind of discovered these things independently, and we're thinking about these K-core partitions for like, I don't know, probably like 6 months or something before we realized that like they are an object that actually has a name and that people have been studying for years. So there's actually a lot of literature on these K-core partitions once you know where to look. And so here's our combinatorial reinterpretation. So let's see, let C comma phi be a general element of the Hurwitz space. Then first of all, I should have said the K-core partitions, much like ordinary partitions, form a lattice. And this is the thing. We spent months trying to prove this, and is already known if you know that these things are called K-core partitions. Okay, so anyway, so the codimension of the splitting type locus is equal to the rank of lambda mu in the lattice of K-core partitions. Which I should say is not the same as the number of boxes in the K-core partition. So this is a little bit more subtle than the statement I said earlier in the talk. And also, so similarly to the standard setting, so if the expected dimension is 0, then the number of points in the splitting type locus is equal to the number of maximal chains in this lattice that start at the empty partition and go up to the partition lambda mu. So this is that I said that there was like a way to count these numbers, and this is the way. I'm pretty sure that no one has been able to write down a closed form expression for these numbers, but that's fine. Okay.
Are there also some, like a bijection with some tableaus that you can write down here, or does it not exist?
Yeah, exactly. So if you have a chain in this lattice of partitions, then you can produce from that a tableau by just you write the number k in all of the boxes that appear in the kth partition in the chain that don't appear in the k minus first partition in the chain.
Okay.
And so in these cases, the tableau that you get have, I shouldn't have used k because that means something else in this talk, but you get partitions where the same number can appear more than, in more than one box. But yeah, you still get tableau. You just don't get standard tableau.
Right.
So maybe actually, okay. Ooh, I've been flying through this. So maybe I will pause here for a second see if anyone has questions before I go on to the next unrelated topic. All right, well, if not, I will talk about some stuff that is not related to stuff that Kaylin and I have worked on, but it is sort of in the same general theme. So you can see on this slide I wrote time permitting, because it's been years since I've given a Beamer talk, and I had no idea how long this was going to take. So, okay. So this is the extra stuff I prepared in case that only took half an hour. So I want to also talk about the Prym setting. So the Prym setting is when you have an étale double cover of a curve. So for the rest of this section, I'm going to let C twiddle, whatever, be a C twiddle to C be an unramified double cover of a curve. Okay, where the base has genus G. So then the Prym-Brill-Noether varieties, which I think were first defined by Welters, are these things. So you look at the set of line bundles on the curve upstairs, whose norm is the canonical bundle, that have at least r+1 independent global sections. It turns out that that's, if I stopped there, that would be, that would have two components for like parity reasons. So I also insist that the number of independent global sections is congruent to r+1 mod 2. Okay, so that's what a Prym-Brill-Noether variety is. And just like in the previous two settings, there's a bunch of standard results about these Prym-Brill-Noether varieties when your unramified double cover is general. So if you take a general unramified double cover where the base is genus G, then you can say all of this stuff. So the Prym-Brill-Noether variety has pure dimension G minus 1 minus r+1 choose 2 when this is non-negative and it's empty otherwise. This is proven, I think, independently by Welters and Bertram in the 80s. Again, the locally closed variety, where you take out all of the all of the line bundles that have strictly more than r+1 global sections, is a smooth variety. So if the expected dimension is at least 1, then this thing is irreducible. And if the expected dimension is 0, then you have this closed form expression for the degree of the variety. So again, you have a similar set of results to the standard Brill-Noether theory results. These also have combinatorial interpretation in terms of partitions. So if you let delta R be the isosceles triangular partition, so it has R boxes in the first row, and then R-1 boxes in the next row, and then R-2 boxes in the next row, and so forth. So you get a triangle. Really I should have drawn a picture. Then you can recast this by saying that the codimension of VR C pi in the Prym variety is equal to the number of boxes in this partition, or equivalently, it's equal to the rank of this partition in the Young lattice. And if the expected dimension is 0, then the degree of this variety is equal to the number of standard Young tableau on this partition, or equivalently, it's equal to the number of maximal chains in the Young lattice that start at the empty partition and go up to this. So again, we see the same, very similar kind of combinatorics arising in yet another setting, right? And so, okay, so more recently, various authors have thought about the case where you have an étal double cover of a curve C, but the curve C is not general. In particular, like what if the curve C itself has a map to P1 of small degree K, right? So, so in this case, when K is even, this triangle that I described is a K-core partition. It's not hard to see, but I haven't given you any of the definitions, so it's probably hard for you to see in this moment. And so here's a theorem due to, well, all the authors on the screen. So Yoav and Martin, and also Yoav and Creech, Ritter, and Wu. So if you have an unramified double cover of a general K-gonal curve, Oh, okay, the way that I've written this, it only makes sense when k is even, but they have a result for all k. So then the codimension of the Prym-Brill-Noether variety in the Prym variety is at least the rank of this partition delta R in the lattice of k-core partitions. And so, you know, so what we're seeing is it's sort of a combination of the previous two results, right? Like in the Prym setting, you get you get the rank of delta R in the standard Young lattice, and in the k-gonal setting, you get the rank of some partition in the lattice of k-core partitions. And here, when you combine the two, you have this Prym-Hurwitz setting. You get the rank of delta R in the lattice of k-core partitions. And then, yeah, unfortunately, there are cases sort of when G is sufficiently small in comparison to K, this bound is not sharp. But one could conjecture that the bound is sharp when G is sufficiently large in comparison to K. So it's still an open question for which values of G, R, and K this bound is sharp. And you know, I put that question to all of you. Okay. Okay, and I guess that's all that I prepared. So I'm going to end a little bit early, but I'm happy to take whatever questions if you have. So thank you for listening.